Let us a brief introduction. I think you already know me. Okay, so I have done MTech from IIT Kharagpur. I have done MSc from Politecnico di Milano. I have around 5+ years of teaching experience, and my year score was 675 last time. Okay, chalo. Should we start? Should we start, or should we wait? It's already 8:53, so I'm not sure if we should wait. Let us start. Sahil is going to join late because he is in office. And other people can join later. It's fine. ठीक है? चलो. Let us start. Okay, Shruti has also joined. How are you, Shruti? How's your preparation? Chalo. So what we are going to discuss, we are going to discuss unsteady state heat transfer. And whenever we talk about unsteady state, we already know. What do we already know? That whenever we talk about unsteady state, temperature is a function of time. Temperature is a function of time. So if we have a body, let's say we have a body. So let's say we take an element here, any element. Okay. And what did we assume? We assumed, yes, temperature vary with time. We assume that if some heat Q in is entering, some Q generation is happening, and some Q out is happening. So energy balance, what was the energy balance? Q dot in, okay, plus Q dot generation is equals to Q dot out plus energy storage, which was this. Okay. Yes. In out generation plus U, change in U. Okay. Very nice. Now, generation, look, we started with what? We started with 3-dimensional steady state and without heat generation. Without heat generation. Now, in the last class where we talked about, I think it was a third class, what did we talk about? We talked about 3D, 3D, and 1D, right? We also talked about without heat generation and with heat generation, how to deal with problems with and without heat generation. But during that day, during that class, we never assumed unsteady state. All the cases were steady state. So now it is time that we also talk about unsteady state. Unsteady state. Okay. So in this scenario, we are going to assume that there is no heat generation. Okay. So this is basically zero. This is zero. Okay. And if you solve this, it is Q in is equals to Q out plus rate of change of internal energy. Okay. And this was our general equation. This was our general equation, which we already defined. Okay. Now, when we are saying unsteady state, it means that energy in is not equal to energy out. There is some energy stored inside the body. Okay. And because if a body is there, energy, it will store in mass. If mass is there, it can store some energy. Okay. And because it is storing some energy, it can store in the form of internal energy, potential energy, kinetic energy. In these three forms, any mass can store energy. Here we neglect these two changes. So the only change, if energy is stored inside the body, then the only change that will happen is internal energy in the system. Okay. So it is going to, whenever we talk about transient or unsteady state, we have to account for the change in internal energy of the body with respect to time. Okay. So this is my general equation. Now what I am going to assume that it is first of all one dimensional. So it is happening either in X or in Y or in Z direction. Let me assume it is only, temperature is only a function of X. I am assuming this. It could be Y, it could be Z as well, but I am assuming it is only varying in the direction of X. That means this will be zero, this will be zero. Temperature is not changing in Y and Z direction. Okay. Also, I am saying without heat generation, that means Q generation is equals to zero. that means it will also be equal to 0. Now what is my equation in this particular condition? D square t by dx square is equals to 1 upon alpha dt upon d tau, change of temperature. Now this term is showing me that it is a unsteady state heat transfer. Unsteady state heat transfer. Okay, so I have simplified my general equation in by applying these assumptions. Okay, is it clear? This much is clear. Yes or no? Okay, chalo. Let us move on. Now, what is my equation? My equation is, first of all, one dimensional, unsteady state, and no heat generation. So my equation is d square t by dx square is equals to 1 upon thermal diffusivity change in temperature with respect to time. Okay, chalo. Now let us consider a plate of thickness 2L. Okay, so here x is equals to 0, here x is equals to minus L, x is equals to plus L. So whole thickness is 2L. Okay, and this whole body I have maintained at a particular temperature, let's say T initial. Okay, this whole body is maintained at T initial. Okay, so let me say at time is equals to 0 second. Okay, at time is equals to 0. In fact, let me define time is equals to 0 at after a particular statement. Now what I am saying, look, this body I have maintained at Ti. How I have maintained at Ti? For example, I have put it in a furnace. So because of the furnace heating, this body is uniformly heated to a temperature Ti. Okay, now I have taken out of the furnace and I have left it in a surrounding, which is air. So air temperature is T infinity. Okay, so what will happen, look, this heat will be if I have exposed it to a air, then air will flow and take away heat from this, so whatever temperature is there, some Q convection will happen from both sides. Q convection will happen at both sides. Q convection will happen. Okay, so it will happen, first of all, look, whatever temperature. Now how the cooling will happen, look, this surface is going to be cooled first. The outer surface is going to be cooled first, right? And for example, at center the temperature will remain Ti for a longer period. So now there is a temperature difference between the center at x is equals to 0 and x is equals to minus L and plus L. So that means there is a temperature difference between the center and the extreme ends. So here conduction will also happen, right? Conduction will also happen because of the temperature difference. Is it clear? Is it clear? Chalo. Now conduction will happen, right? So let me assume when I have not dipped or when I have not taken out this body from the furnace at that moment. Okay, so for example, I take it out and when I keep it in air at that instant, at the moment I have put it here at t, that is t is equals to 0 seconds. Okay, the moment, for example, you have a hot ball and you put it in a water tank. So the moment that you are putting that ball into the water tank, that moment the whole body is at Ti. So at T is equals to 0, the whole body is at initial temperature. T is equals to Ti. Is it clear? Is it clear this much? And also I can say that X is equals to plus minus L. क्योंकि अभी तो मैंने I have just taken it out. अभी तो I have just taken it out from the furnace. So the whole body is at ti, चाहे आप center की बात करो, even if you are talking about center or at the boundary, the whole surface is at ti. Okay, now what is second thing? At t is equals to tau second, at t is equals to tau second, at t is equals to tau second, can I say dt by dx is equals to 0 at x is equals to 0? ये आपको, आर यू एबल टू अंडरस्टैंड दिस कंडीशन? at the center at the center temperature is maximum. Are you able to understand this situation? Shruti, is it clear why we are taking dt by dx is equals to 0 at x is equals to 0? Because the temperature is very whenever you are taking anybody out or you are dipping anybody in a cooler medium, so what will happen? Heat transfer will take place from the center towards the outer radius or outer boundary. So the center will be maintained at the highest temperature because the heat is the heat is convected out from the boundary. Okay, is it clear, Shruti? Sean says yes, so I am assuming it is clear to both of you. Chalo. So this is condition. Or can I also say that at t is equals to t seconds, tau seconds, q dot conduction is equals to q dot convection at x is equals to plus minus L. Is it also clear? By at आप इस बाउंड्री पे ले लो और आप इस बाउंड्री पे ले लो, whatever boundary you are taking, conduction is equals to convection. Whatever heat is conducted out at the boundary is taken away by the fluid. ठीक है? Is it clear? So we have three boundary conditions. Sean, is it clear? No, that unsteady state is what? Temperature is changing with respect to time. So abhi I was about to come at the topic. What is happening here? Okay, I'll tell you this in some time. But can I say, look what, chalo, theek hai, I'll explain this. See, here temperature is Ti. Now temperature is decreasing like this. It is decreasing like this. So here, let's say it is T dash. Here it is T double dash. Here it is some temperature. But whatever heat is conducted here at this point, it is taken away. It is taken away by the fluid. So temperature is changing inside the body with respect to time, isn't it? So it is unsteady state. आया समझ में? Okay, ठीक है. At the boundary, I am not talking about inside the body. Temperature is changing with respect to time. Okay, similarly it will happen at this side. Okay, so whatever heat is conducted will be convected away. ठीक है, so this is my condition. Now let us assume theta. What is theta? Theta is equals to t minus ti. What is t? T is any instantaneous temperature at any time t. Okay, किसी भी एक टाउ सेकंड पे जो टेम्परेचर हो रहा है at any time tau seconds, whatever the temperature is there is t, and ti is the initial temperature at x is equals to 0. Okay, so can I also say d theta by dx is equals to dt by dx? Can I also say d square theta by dx square is equals to d square t by dx square? So by substituting this in my first equation, can I write d square theta by dx square is equals to 1 upon alpha dt by d tau. Okay, so this is my differential equation under these conditions. Okay, is it clear? Okay, now let us move on. So d square theta by dx square is equals to 1 upon alpha dt by t tau. Okay, this is my Now again, whenever I solve this, I'll get a solution will be in terms of, it is a function of two constants C1 and C2. Okay. Although I'll tell you what I am doing, but I do not need to show you the solution. Okay. When you start solving it, it is a complicated analysis. Why? Because temperature is varying with time. You see this temperature is varying with time, and this analysis is really complicated, really complicated. Okay, now what we are going to do is we are going to simplify this. Now, in order to find the C1 and C2, we apply the boundary conditions. We apply boundary conditions to find out C1 and C2. And now we need to determine the temperature distribution equation. The whole aim is to determine temperature distribution equation. Why do we need temperature distribution equation? It will tell you at any what is the temperature at any x. किसी भी एक point पे at any time what is the temperature, that will tell you by using temperature distribution equation. Okay, now I will tell you this analysis is very complicated. We do not need to do this analysis is very complicated. If you want to refer, you can refer it from the book, but I am telling you, it is not at all required. It is not required. No one does this for gate. Okay, analysis is very complicated, so we need to simplify it. Okay, now simplification result, I am going to give you the temperature distribution. So when you simplify it, again, it is not the actual equation, but we need to simplify it by using error function. With some error, we are going to accept the result. So what is the equation? It is T minus Ti upon T surface at the boundary, okay, is equals to error function x by 2 alpha time t. Okay, so this is your temperature distribution equation. Okay, now what we are doing here, we are accepting the result with an error function, Now I'll tell you, till now till this date, till this year, only once they have asked question based on this condition. Okay, unsteady state problems are not solved like this. I'm going to tell you, and we are going to see the questions as well. You are going to practice questions as well, but you will see one thing. Okay, only once they have asked the question that is solved by this equation. Okay, now what do we do 99%? You see, look here, what we are saying, if this is the body, and let's say this is the center. Okay, and it is a hot body. Let's say it is a hot body at initial temperature Ti. Now the variation of temperature is basically a function of time. Okay, so temperature, this whole body, you see, if I say at this boundary Q conduction is equals to Q dot convection. But this Q conduction inside the body is changing because the temperature is changing by minus Ka dt by dx. This dt by dx is constantly changing. Inside the body and with respect to time as well. This temperature is a function of time. This temperature is a function of x and time. Okay, and that is why this analysis is very complicated. Very complicated. So in order to simplify this, what do? We assume that my whole body is at fixed temperature. Okay, this whole body is maintained at a fixed temperature Ti. Whenever heat transfer is happening, this whole body is at initial temperature Ti. Okay, it is at constant temperature. Okay, It is to simplify this condition of unsteady state. It is to simplify the condition of steady state. Sean, is there any confusion? Are you trying to say something? Should I wait for you? Yes, yes. Look, what Ti is the temperature, the initial temperature. Okay, but at the center, Ti will remain for a longer period. But as you go from the center to the boundary, this Ti start reducing to a lower temperatures. Okay, so temperature is changing with X and with time, both the thing. Yes, of course, Ti will reduce. Of course, Ti is going to change, but that is what we are going to assume, that whatever the temperature is, for example, at t is equals to 0, at time t is equals to 0, the whole body is at Ti, and at time is equals to, at 1 second, what I am going to assume, I am going to assume that at time is equals to 0, the whole body is at Ti, and then at time is equals to any tau seconds, this whole body is at different temperature, let's say T double dash. Okay, then if the time is changing, the whole body temperature, so whatever is changing, the whole body temperature is changing. The whole body is at constant temperature at any time, at any time. Okay, okay. So what I am saying, temperature is not changing with X. Temperature is not changing with X. It is only changing with time. And this will satisfy our unsteady state assumption as well. Okay, because temperature must change with time. Okay, chalo. So what I am saying, whatever the temperature is, either it is Ti or it is something else, some intermediate temperature T, but the whole body temperature is same, the whole body temperature is same. Okay, chalo. That is called as lumped heat analysis. Why we do lumped heat analysis? Lumped heat capacity is based on uniform temperature throughout the solid body. You see, look, you have this body. Now, here temperature is Ti, here temperature is, let's say, Tw. Okay, and Ti is greater than Tw. So, what will happen? First of all, conduction will happen. First of all, conduction will happen, Q dot conduction. And then convection will happen, Q dot convection. Okay, yes. Now, if I am saying my whole body, here also Ti, here also Ti. So, because there is no temperature difference inside the body, so there is no conduction. There is no conduction. Only convection will happen. Only convection will happen. Now this is an assumption that we are assuming that the whole body is at Ti. This is an assumption that we are taking. When this assumption is valid, that is also true. No, if you are assuming something, you must assume there must be realistic assumptions. Okay. So now when this can happen, when will this happen? It will only happen if the conductivity of this body is really, really, really high. Why? Why conductivity is high? Because if the conductivity is high, then the heat transfer will happen instantaneously. The heat transfer will happen instantaneously. Also, thermal resistance, conductive resistance is L upon Ka. I am taking for a rectangular body. If you want to take a sphere or a cylinder, you can take. What is for sphere? Ln R2 by R1, 2 pi KL. But what I am trying to tell you is thermal resistance is inversely proportional to K. If K is very, very high, thermal resistance is very, very low. That means whatever heat is there, it will be instantaneously transferred outside. This body will not, its conductivity is so high that whatever heat is there inside the body, it is instantaneously transferred outside, and there is not enough time with the body so that its temperature may change. Okay, is it clear? Are you trying to imagine when can it happen? John, I am waiting for you. You are typing something. I am assuming if you have some doubt. Temperature difference is neutralized fast due thermal conductivity. Temperature, I don't know if what you are trying to say, but yes, what I am trying to say is, look, if the conductivity is very, very, very high, okay, so the temperature difference, you see, what is Q dot conduction? Q dot conduction is minus Ka delta T by thickness. Okay, now thickness, whatever thickness is, it does not matter much. Okay, but if conductivity is really, really high, then for a given heat transfer, dt will be very, very low. That means the temperature difference is not very significant. Okay, so if temperature difference is not very significant, so we can assume that the whole body is at the same temperature. Okay, is at the same temperature, and we can assume this. Now it's very important to understand that this assumption is only valid for bodies which has much higher thermal conductivities. For example, for a steel ball, you can take this assumption. You can apply lumped heat analysis. But for example, if you put a potato, for example, you have boiled a potato, okay, and it is very hot. When you take out the boiling water, it is very hot, and then you put it in a water. Now you cannot use lumped heat analysis. Why? Because the conductivity of potato is very, very low. So you cannot use this analysis. You can only use this analysis for a body which has relatively high thermal conductivity. Okay, chalo. So thermal conductivity of the body is infinite, and therefore internal conductive resistance is very low, very low. Okay, so what we are assuming this, and K is infinite, thermal conductivity is 0. So these points are very important. These points, every point is very important. First, lumped heat analysis is based on the assumption what? We assume that the whole body is at the constant temperature. First thing. Second thing, when can this happen? This can only happen when when the thermal conductivity of the body is infinite and the thermal resistance, conductive resistance is very, very low. So internal conductive resistance is very small, then only you can assume that lumped heat analysis is valid. Huh. Now such this condition is not valid, such materials is not available. This is done to simplify transient heat conduction problem with acceptable accuracy. Okay, so we all know that there is no body that has infinite thermal conductivity. But why do we do it? It just to simplify our transient or unsteady state condition problems. Okay, chalo, this is why we need to do it. Now let us move on. So you see, consider a heated solid body of mass m. Okay, आपने एक body ली इसका mass m है. You have taken a body whose maximum for diamond, yes, but again not infinite, right? It has 2300 watt per meter Kelvin, but still it is not infinite. ठीक है? And its initial temperature is Ti. Now it is suddenly exposed to a ambient fluid. For example, water is there. Okay, so water is at T infinite. Now, as soon as you dip it into the water, Ti is the initial temperature of the body at time is equals to 0 second, and T is equals to T temperature of body at any time tau seconds. Okay. Now, when you have dipped this body, so what will happen? Again, I am assuming lumped heat analysis. Okay. So this whole body is at T initial, first of all, and then whatever heat is convected, it is only convected. The heat transfer is only convection. So whatever heat is taken away by convection, it is going to reduce the internal energy of the body. Why? Because bhaiya, it is at Ti, right? It is at Ti. After some time, this temperature will reduce to T dash. Okay, Ti is less than T. For example, it is 0 seconds, then tau seconds, tau or 5 seconds, let's say 5 seconds. Then T double dash at 10 seconds. Okay, so the temperature is reducing, and if the temperature is reducing with respect to time, that means the internal energy of the body is reducing with respect to time. Okay, So the rate of heat convection, heat transfer between body and fluid, whatever heat is taken away by convection, it is responsible for the rate of decrease of internal energy of the body. Okay, chalo. So what is the convective heat transfer by HA? T minus T infinity. What is this T? T is that instantaneous temperature at any time T. Instantaneous temperature at any time t. Okay, agar main dekhu what is the temperature at 5 seconds, so that is t. After 10 seconds, what is t? Whatever the temperature at any instantaneous time is basically t. T dash, what you say? Yes, t dash. After 5 seconds, it's t dash, and then after 10 seconds, it's t double dash. Yes, and this is the decrease in internal energy of the body. Let's say c, not cp, c. Okay, dt by d tau. Okay, chalo. Now, it will only happen, for example, when a hot steel ball were immersed in a cool pan of water. So, you can only apply lumped heat analysis because the steel ball will have higher conductivity. So, I can assume that the internal conductive resistance in the body, what can I assume? I can assume that the conductive resistance in the body is very small. So this is R convection, this is R conduction. Now because conductivity is high, I can say that internal convective resistance is much lower than external convective resistance. So then only if you can prove this, then only you can apply lumped heat analysis. Okay, and it is to simplify unsteady state heat transfer. Okay, chalo. Now, so now I need to determine temperature distribution equation in this particular condition. Okay, chalo. So you see what we have assumed. Look, as the temperature is not uniform. Okay, not uniform. हमने क्या माना है? Temperature is not uniform inside the body. Therefore, we have to simplify our analysis using lumped heat analysis. Lumped heat analysis. Okay. And हमने क्या देखा है lumped heat analysis में? What have we seen? Good evening, Sahil. Good evening. Chalo. What have we learned? That by whatever Q dot convection is there, it is going to reduce the internal energy of the body. Okay. Chalo. What is Q dot convection? By HA, T minus T infinity is equals to minus mc dt by d tau. That is what we have seen earlier. Okay, chalo, let us try to simplify this. Okay, can I write ha by mc? For m ko what can I write? M, mass is equals to density into volume. So let me write density into volume. Okay, chalo. Then I can take this here, d tau. And here I can write dt by t minus t infinity. Okay, chalo. In order to find out a total heat transfer, what can we do? I can integrate this. How the temperature, in order to find the temperature distribution equation, I can. And this is changing from 0 to any tau seconds. Okay, and this is changing from initial temperature to any temperature t. Okay, ठीक है. So I can write HA rho into volume into C into tau, right, is equals to minus ln T minus T infinity upon T initial minus T infinity. Okay, is this clear? Any confusion in the integration? Chalo. Now what can I do? I can do that HA upon rho into volume into C into tau is equals to, I will remove the sign minus here and I can swap the numerator and denominator. just for my convenience. There is no other reason. There is no other reason. Now I can take exponential on both sides. So finally I am going to get ti minus t infinity upon t minus t infinity is equals to e to the power ha upon rho volume. One second. Rho into volume into c tau, into c tau. Okay, and we all know what is a, is the surface convection area, right? Surface area, area of heat transfer. This is volume of body, volume of body. Okay, c is heat capacity, specific heat capacity. Okay, this is meter square, this is meter cube, this is joule per kg Kelvin, and t is time, any instantaneous time. Okay, is it clear? Is it clear? Yes or no? Chalo. Sahil, Shruti, are you there? Tell me, is it clear? Any doubt? Sahil has joined late, but ठीक है, you can see the okay, ठीक है. Anyway, what we are doing now is much more important than what we have done before. Okay, 99% will question will solve from what we are doing now. We have done our analysis earlier. 1% question can come from there, but what we are doing now is much. This equation is, you see, your 99% question will be solved. 99% of the question will be solved from this equation itself. Okay, so Sahil, be happy, you have not missed anything. You have missed only 1% of it. Okay, 90. I'll do some questions today, and you will understand that 99% of the questions will be solved from this equation if it comes from unsteady state. Okay, chalo. Now, so this is my temperature distribution equation. Okay, this is my temperature distribution equation. Now, what is this equation telling me? Look, this is temperature distribution. How temperature is changing with respect to time. So can I say for unsteady state heat conduction and without any heat generation, this is also a condition, the temperature of body changes exponentially with respect to time. Changes exponentially with respect to time. Can I say this? It is showing me, the equation is showing me the temperature distribution is exponential. Okay. Now, you see what actually happens is, I'll tell you what does it mean? What does it mean? You see, look, how do I tell you this? Yes. So let's say you have, you have just boiled something, or for example, like you have cooked something. You have cooked something, right? And the moment you switch off the flame and you touch that body, it is very hot. Rate of temperature decrease with time. Yes, it is there. No, what do you mean? Exponent? No, it's not. It's not important that it is changing with decrease with time. You can do heating as well. Heating is also,
Hello, sir.
because you see, I'll tell you one. Let me just wait for me. I'll explain this. But it reduces exponentially or increases exponentially. What does it mean? Let's say you have, you have just cooked and you have reduced the flame. Okay, and you touch that body, it is very hot, right? Now what do? You touch that after 2 minutes, so it is comfortably hot. Then you touch that after 5 minutes, it is still hot, but you can comfortably touch it. And then as the time will go on, it will remain hot for a much longer period, but during the initial time it reduces at very exponential speed, and that speed will start reducing. Okay, how do I show this? For example, this is your temperature and that this is time. Okay, and you are heating a body. Let's say you are heating it. So the graph will be exponential. Your graph will be exponential. Okay, for example, you are heating it with a body. That is at temperature 100 degrees Celsius. Okay, and the temperature here is 25 degrees Celsius. Now, because the temperature difference is more, heat transferred will be more. Temperature will change much faster. You see, in this region, initial region, when you are heating, it is very, very fast heating, very fast heating. But as this temperature is going to increase, at this temperature is going to, for example, now you have reached to 90 degrees Celsius. Now from 90 to 100, in order to reach from 90 to 100, it is going to take much, much more time because temperature difference is less. Okay, so if I talk about this region, this side, it is slow heating, slow heating. Okay, you can also see that, you can also show it like this. Look, for a in the initial level, because temperature difference is very high, in very small duration of time dt, look, the temperature difference is really, really high, isn't it? What is this? This is dt by dx. In a very small time, in a very small time, the temperature difference is really, really high. But if you keep on heating, the temperature difference is going to reduce. So if we talk about here, let's see, for a very small time, the temperature difference is also very low. Are you able to understand this? It is going to exponentially change. So exponential is what? In the initial level, it is going to exponentially increase, but after some time, it will remain, that rate of change of temperature will be very, very slow. Okay, is it clear? Is it clear? So here temperature is changing exponentially with time. Similarly, the similar thing happen when you are cooling. The similar thing happen when you are cooling. What will happen? What will happen? You see, it will cool like this. It will cool like this. 1 second. It is not exponential. It is going to cool like this. It is also not exponential. I am really sorry. It is, let's say, like this. Okay. Now, for example, you started from here. You are cooling. You started from here. In very small duration, for example, in this time, it is very fast cooling, fast cooling. You see, the graph is dropping like anything. But if you come here after a certain time period, after a certain time period, you see now the graph is not decreasing at a very high speed, not decreasing exponentially. Okay, so this is slow cooling. It is slow cooling. And you can also show this by using the slope. How do you show it by slope? Look, for a very small time, this much temperature difference is obtained. This much temperature difference is obtained. But here, for a very small time, for the same time, the temperature difference is very low. So as the time goes by, the rate of heat transfer, the decrease in temperature or increase in temperature reduces. Okay, in the very initial period, the temperature difference is really, really high. It will increase exponentially. But as the time goes by, that you will have to give much more time to, for the same amount of temperature increase or decrease. Okay, is it clear? And you can also see that here dt by dx is negative as x is increasing. I'm sorry, dt by d tau. I'm sorry, dt by d tau. dt by t. As time is increasing, temperature is reducing. And for heating, dt by d tau is positive. It means as time is increasing, temperature is increasing for heating. And this is for cooling. This is for cooling. Is it clear? So again, if the question says in unsteady state heat transfer, the temperature varies logarithmically, exponentially, parabolically, linearly. What is the answer? Exponentially. Very nice. Okay. And you can also experience this in your real life. In your real life, you see, you the hot when you start drinking the hot coffee. For example, you are making tea, and you have just, what do you call it, छानना जो कहते हैं, filter or whatever you have done. So as soon as you filtered that tea, if you start drinking, it's very, very, very hot. But if you just wait 1 minute, if you just wait 1 or 2 minutes, it is comfortably cold to drink. But you can, so for example, when you that filtered, that the temperature was, let's say, 60 degrees Celsius. Okay, at time when you have filtered it. But if you only wait for 2 minutes, it will reduce to around 30 to 35 degrees Celsius, 30 degrees Celsius. But after even 10 minutes, you will see that it is at 20 or 15 degrees Celsius. You see, so in only 2 minutes, there is a temperature difference of 30 degree. And in this 8 minutes, it is only decreased by 15 degrees. Okay, so this is unsteady state heat transfer. Is it clear? Sahil, Shruti, any doubt, anything, any problem with this? Okay, very nice. Chalo, let's move on then. Let's move on then. Chalo. Now there is a concept of time constant here. Time constant here. Now let us see what is time constant. So some objective questions or even time concept constant is something that you are going to use in most of the numerical. I would not say every numerical, but most of the numerical. Okay. First of all, you have to understand this is the most important equation of unsteady state heat transfer. You should never forget this. 99% of the question will come from this. You will have to use this equation and solve the question. Okay, without any doubt. Without any doubt. Okay, chalo. Now you tell me one thing. You tell me one thing. What is the unit of this? What is the unit of this? Yes, this is dimensionless. Very nice. Dimensionless. So what will be the unit of this? Yes, again, of course, they are equal. So it is also dimensionless. So in order for this to be dimensionless, what must be the unit of this? This must also be dimensionless. Okay. Yes. Now, if I want this to be dimensionless, how can this be dimensionless? Because I know that H has a unit, A has a unit, everything has a unit, right? So, but what do I know? That this tau is what? It is time, and the unit is second, and the unit is second, right? Now, this whole quantity, if this whole quantity has a unit of 1 upon second, then I can say that this could be dimensionless. Can I say this? Is this okay? Okay, now let us term this as a constant b or b star. Okay, it is a constant b star, and its unit is 1 by second. Its unit is 1 by second. Now, so can I define a term, the reciprocal of b star, the reciprocal of b star has a unit. क्या होगी अगर मैं कहूं रेसिप्रोकल ऑफ बी स्टार? बी स्टार का रेसिप्रोकल जो होगा, व्हाट विल बी द यूनिट ऑफ दिस? Yes, as a unit second, and it is called as time constant t star. Okay, this is tau. Do not confuse. This is tau, and tau star is time constant. So tau star क्या होगा भैया? Rho vc upon ha. Rho vc upon ha. Is it clear? Is it clear? और इसकी यूनिट्स क्या होंगी? What is the unit? Second. Units will be second. Okay, chalo. Now, can I write it like this? You see, 1 upon ha into rho vc. Rho v, and v, what is v? Can you tell me what is v here? Do not forget what is v. V is volume. Yes. So what is this quantity? What is this quantity? 1 upon ha into, what is this quantity? Rho into v. What is rho into v? Mass into specific heat. तो अब ये बताओ, tell me what is this? What is this? 1 upon ha. Do you remember this term? Do you remember this term 1 upon ha? Yes, it is thermal resistance. 1 second. It is thermal resistance. And can anyone tell me what is this, bhaiya? Can you tell me what is M into C? M into C. Yes, it is the heat storage capacity, or I can say is thermal capacity as well. Thermal capacity. Okay, chalo. So can I say tau time constant is equals to thermal resistance into thermal capacitance? I can say this, right? Now tell me one thing. I am saying thermal resistance is high. Thermal resistance is high. Okay. So tau will be high, isn't it? This will be high. Or I am also saying this is high. Or let me explain this in some other way. Okay. I am saying thermal resistance is high. What does it mean? If I say this body has a higher thermal resistance, so heat conduction or heat transfer will be high or low. If I am saying thermal resistance is high, so heat transfer will be high or low. Heat transfer will be high or low. Very nice. So heat transfer is low. Now tell me, if I am saying thermal capacity is high, if I am saying thermal capacity of a body is high, thermal capacity is high, so heat transfer will be high or low? Heat transfer will be high or low? Anyone else? Sahil, Shruti. If I am saying, yes, Sahil is saying low, Sean is saying low. Shruti, if I am saying any body has a high thermal capacity, what does it mean? It means it can store more and more heat. Yes, low resistance is okay. Low resistance is ठीक है. Low, yes, it can low resistance is a different thing. Okay, low resistance will depend on conductivity. But even if conductivity is happening, heat is getting conducted inside the body. But body has high thermal capacity. That means it will store more heat. It will store more heat in the form of internal energy. It will not allow heat to pass away. Yes, yes, very nice. Ceramic glass example, very nice. Okay, so it will not allow heat to pass away. So heat conduction or heat transfer will again be low. So agar this is high, that means more and more heat can be stored in the body without transferring. Now if it is stored, what is increasing? Internal energy is increasing. Heat is not going out. Okay, so it is low. Again, heat transfer is low. That means if this is high, you see thermal resistance is high, thermal capacity is high, that means this is also high. So if tau is high, that means either heat is not getting transferred or more heat is getting stored. That means high value of time constant means low response to heat transfer. Low response to heat transfer. Okay, and similarly low values of time constant means ki thermal resistance will be low, heat or thermal capacitance will be low. That means more and more heat will transfer. And if I say low values of time constant means fast response. Instead of low, let me write slow. Instead of low, let me write slow response. Slow response means what? I have given you the example of that wall as well. Yes, I have given you the ceramic wall and steel wall. You will not feel the heat on the other side if capacity is high. Okay. So fast response to heat transfer. Is it clear? Is it clear? Fast response to heat transfer. So what is the significance of time constant? It tells you that if the body will be able, if I calculate time constant, and low value of time constant will tell you slow response to heat transfer. Oh, sorry, high values of time constant will tell you slow response to heat transfer, and low values of time constant is fast response to heat transfer. Okay, chalo. Now, time constant is defined as the time required to decrease or increase temperature by 63.21% of initial value. Larger value of time constant signifies that the response will be slow. Okay, kitna time, how much time it is going to take to reduce this value to 63%? Okay, to reduce 63% of the initial value, so how much we have to reduce? Around 36% I have to reduce the temperature. Okay, so let's say this is my equation. Okay, now if, first of all, tell me tau star is what? Tau star is what? Rho v c by ha. Okay, so can I write this as t minus t infinity upon t minus t infinity is equals to E tau upon tau star? I can write this. Now, if tau is equals to tau star means t initial minus t infinity upon t minus t infinity is equals to e to the power 1. E to the power 1. So how much is this? T minus t infinity upon t minus this is equals to, it is around 2.718. And if I do a reciprocal of this, I can write t minus t infinity upon ti minus t infinity is equals to 0.63678. Okay, I can also write this. Now this is what? This is initial temperature difference. Whoa, this is instantaneous temperature difference at a particular time. At a particular time, what is the temperature difference? At a particular time, instantaneous temperature difference at any particular time is instantaneous. And this is initial temperature difference. Okay, so now if this is equals to 0, it will reduce to 36%. 36%. So temperature is reduced by, now this time the instantaneous temperature difference is 0.36, yani 36% of the initial temperature difference under this condition. Okay, so the temperature difference is reduced by, kitna reduce ho gaya? 63.21% of the initial value. Okay, the definition is important in this. They will, although it is not very common, but if they ask the definition of time constant. How do you define it? Okay, is it clear? Chalo. Now let us talk about some dimensionless numbers. Okay, first of all, now you need to see this as well. Now I have told you this equation you are going to use very, very, very frequently. Okay, so most of the things, h will be given to you. Okay, as c will be given to you, density will be given to you. Okay, h will be given to you, c will be given to you, density will be given to you. The problem that will come is volume per unit area I need to calculate. Now it will depend upon what kind of body there is. So if there is a sphere, so I know that I can calculate V by area by volume is what? What is the volume? What is the volume for a sphere? What is the volume? 4 by 3. Yes, very nice. And the area is 4 pi r square. So this will be r by 3, or I can also say d by 6. Okay. And again, 90% questions will include sphere. So this formula will be applied. Okay. And for cylinder and cube, you can calculate V by A as r by 2 and L by 6. This is how you can calculate this. Okay. And very, very less, I mean, it is very rarely asked these two, but still you need to know. But most frequently you need to understand sphere, because sphere is mostly given in question. I am telling you what is more important so that you can make it a priority to focus on that. Okay, and we will solve the question. You will know also. Okay, I am not just making things up. Chalo, okay. Now let us talk about some dimensionless numbers for unsteady state heat transfer. Okay, first is Biot number. Biot number is defined as internal conductive resistance upon external convective resistance. Okay, so for example, you have a body and it is in some fluid, let's say water or something. Okay, so because there is a temperature difference here, T and Ti, okay, and it is a T infinity. Okay, so how do you calculate internal conductive resistance? LC, this is characteristic dimension. I am specific because here convection is involved. So I am taking uh, characteristic dimension L upon Ka, L upon Ka. And this is 1 upon Ha, 1 upon Ha. Okay, convective resistance is what? 1 upon Ha. Conductive resistance is what? L upon Ka. Okay, is it clear? Okay, now area is same. Area is same. So I can say Biot number is equals to LC HLC by K. And this K is for solid. It is very important. It is very, very, very important that you remember that this K is for solid. This K is for solid. Okay. And LC will be equal to volume per unit area, surface area. Volume per unit surface area. Now tell me one thing. Where if I talk about lumped heat analysis, lumped heat capacity analysis, lumped heat capacity analysis. So what is the relationship between internal conductive resistance and convective resistance? Can you tell me the condition? If I need to apply lumped heat analysis, what is the assumption? What is the assumption? Yes, very nice. Internal conductive resistance must be very, very small to external convective resistance. Okay. But how small? There must be a number, right? We cannot just rely on anything. कि भाई बहुत कम होगा, लेकिन how much? कितना कम होगा? So internal conductive resistance by external convective resistance, this ratio must be less than 0.1. So Biot number must be less than 0.1. Then only lumped heat analysis is valid. Then only you can use the other formulas. Okay. If Biot number is greater than 0.1, that means conductive resistance is significant. You cannot just neglect it. Okay, the temperature difference inside the body, your body does not have uniform temperature. There is a temperature difference inside the body. Okay, or your conductivity is low for the body. In that condition, Biot number will be greater than 1 and lumped heat capacity is invalid. Lumped heat capacity is invalid. Okay, this is first Biot number. Okay, in interviews it's a very frequent question. Okay, what do they ask? They ask what are the dimensionless numbers in unsteady state heat conduction, what is the unsteady state heat transfer, what is the dimensionless numbers in forced convection, in free convection. So you must know what are the dimensionless numbers in unsteady state heat transfer. Okay, chalo. Next is Fourier number. Fourier number. Now Fourier number actually tells you if the heat transfer is unsteady or steady. It draws a line that is it unsteady or steady. Okay, chalo. How do I define this? How do I define this? It is defined as Fourier number is equals to Q dot conduction upon Q dot stored. Okay. Now tell me, if Q stored is very less, if the value of Q stored is very less, it is very, very low, then the heat transfer will be steady state or unsteady state. It is negligible. There is no stored energy. So heat transfer is steady state or unsteady state. Yes, very nice. Okay. So if the Fourier number is very high, so I can say if Q stored, one second. If Q stored is much lower than Q dot conduction, that means Fourier number is very high, and that means it is a condition of steady state. Steady state. Okay. Now, how do I see this? How do I see? Look, let's say you have a body like this. Okay. Now, some heat you are giving, Q dot you are giving, and some heat is conducted out, and some heat is stored in the body. Okay. Let's say this is L, L, and L. Okay. So volume is LQ. Okay. Now tell me, what is the Q dot stored? Q dot is stored. How do you store the heat? How do you store the heat? Can you tell me what is the formula? MCDT. But it is not Q. Yes, very nice, Sahil. But it is not just Q. It is Q dot. That means per unit time. Per unit time. Okay. So mass, I can say density into volume into C into delta T, temperature, upon tau. Okay. So I can say rho L cube C delta T upon tau. That is Q stored. Okay. This much is clear or not? Okay. How do I calculate Q conduction? Are we all know, yaar. How do we calculate Q conduction? Q dot conduction can be calculated as Ka delta T by L. Okay. Now it is K L square delta T by L. L and L will get cancelled. KL delta T. Okay. So let me put this here. What? KL delta T upon rho L cube C delta T by tau. Okay. So delta T gets cancelled, K and K gets cancelled. It is K upon tau. Tau will come in the numerator, this tau. Okay. And rho C L. Rho C L. L square actually. L square. Okay. Now tell me, can if I can write K upon rho C tau upon L square, what is this? What is this? Tell me very quickly, what is this? Yes, very nice. That is thermal diffusivity. Okay. Now I can write F dot is equals to alpha tau L square, and that is how Fourier number is defined. Okay. And I hope you have already understood this. Key, if the Fourier number is very, very high, that means steady state. If Fourier number is low, that means heat is stored in the body. If heat is stored, that means internal energy will change. If internal energy will change, that means unsteady state. Clear? Clear or not? Sahil, Shridev, Shruti, tell me, is it clear? Sahil, any doubt? Chalo, theek hai. The last thing that we need to cover here, okay, I don't need to use this. I've already covered what I need to cover in Fourier's number. The last is Hassler chart. So what does Hassler chart do? It is basically, now there are so many, it is very complicated. So basically Hassler chart directly gives you temperature distribution. If I tell you Biot number and Fourier number, if I tell you Biot number and Fourier number, so there is a chart. It is a chart that combines Biot number, Fourier number, and temperature distribution. Okay, it will relate. So if I tell you Fourier number, for example, I have told you Fourier number, I have told you Biot number. So for example, I have told you one value. For example, this is Fourier number. I have taken Fourier number and Biot number, this one, and combined I'll get my value of temperature distribution. I can directly calculate temperature distribution, this value. Okay, so I can get Ti minus T infinity upon T minus T infinity is equals to some given value, whatever X we have gotten read at this one. So Hassler chart determines the temperature distribution and heat flow rate when conduction and convection are of equal importance. Okay. Now, how are we doing this? You see, if I take this value, so it is this. Okay. Now let us move this. Okay, HA upon rho VC tau. Okay. Now can I write H upon LC by K? Okay. Let me write it like this only. Okay, and this is K upon rho C LC square. Okay. I have basically divided it by K. I have divided multiply. 1 second. Let me. I don't remember what we need to do here, but the one thing that we do is we have divided and multiplied it by K. We have divided and multiplied it by K, and we also have brought LC here. We also have brought LC here. So LC here and LC here. So okay, H area upon rho VC tau. Okay, can I write H? And here let me write A rho VC tau. Okay, now let me divide by K and multiply by K here. Okay, now is this clear? I have only multiplied and divided by K. Okay, chalo. Now what else can I do? What else can I do? I can write this A as L square. I can write this. Can I write this as L square? L square. And can I write this as L cube? L cube, right? So let me cancel this. I will get 1L here. 1L. Okay. So this is what? H by K into K upon rho L C tau. Okay. Now what can I do? I can multiply divide it by L. So LC and LC. Okay. So this is what I have gotten. Although I have made it much complicated because I have not seen it earlier. Okay, I saw it a long time back. But basically we need to divide and multiply by K and L. That's all. Nothing else we are doing here. Okay. But why are we doing it? The problem is why are we doing it? So now tell me, what is this? What is this? No. Yes, that is buyout number. That is buyout number. This is HLC by K. This is buyout number, not 1 by buyout number. This is buyout number. Yes. Okay. Now what is this? What is this? Whole thing. Whole thing. I can also write this alpha tau upon LC square. What is this? Fourier number. Very nice. This is Fourier number. Okay. So ultimately what I have done is I have defined this in terms of Biot number into Fourier number. So by using the same thing, if I substitute it here, I can write Ti minus T infinity upon T minus T infinity is equals to E Biot number into Fourier number. अब these are dimensionless terms. So this will be dimensionless, this will be dimensionless. Okay. If I give you Biot number and Fourier number, you can find out temperature distribution. So basically Hessler chart combines. It tells you the distribution, temperature distribution by using Biot and Fourier number. Okay. Although I have made this analysis much more complicated than it is not this complicated. But because I have not solved it for a long time, it just slipped my mind. Okay. Anyway, there's nothing in there. Just multiply divided by LC and K. That's all. Okay. So that is your Hessler chart. Is it clear? Chalo. So these are the concepts that are more than enough to solve any question in GATE. And we are going to take up the questions and we will see that if we are able to solve it or not. Okay, chalo. Let us move on. Let us move on to the first question. Now, what is it asking? A steel ball of diameter. You see, you have a steel ball. The diameter is 60 millimeter. Is initially in thermal equilibrium at 1030. That means T initial is 1030 degrees Celsius in a furnace. Now it is suddenly removed from the furnace and cooled in an ambient. T infinity is 30 degrees Celsius and convective heat transfer 20 watt per meter square Kelvin. Okay, so it is air only. And then density is given, conductivity of solid of this body is given, specific heat is given, C is given, the time required in second to cool the steel ball in air from 1030 to 430. That means it is an unsteady state heat transfer. Whenever these type of questions will come, whenever time is given in the question or is required to be calculated, that means it is an unsteady state question, unsteady state heat transfer. Okay, so we have seen this type of question, and the equation T minus T infinity upon Ti minus, look, what I have given you equation is this one. The equation that I gave you is T initial minus T infinity upon T minus T infinity is equals to e to the power HA rho Vc into tau. Now what do I know? Look, I know T initial, I know T infinity, I know the final temperature. What do I need to find out? I need to find out how much time it is going to take. I need to find out this T when this temperature is 430 degrees Celsius. Okay, so I know everything. What do I know? I know T initial. T initial is 1030 minus T infinity is 30. And this T is 430 minus 30 is equals to E, and I need to find out HA rho VC tau. So now you can calculate time constant, or you can just put the value here. If you are trying to calculate time constant, then it is rho VC by HA. Okay, so I can calculate what is volume per unit area. What is volume per unit area for a sphere? Volume per unit area for a sphere, R by 3, yes, or D by 6. So diameter is given 60. That is 0.06 by 6. It is 0.01. 0.01. Okay, simple. Chalo. So what can I do? Density is how much? Now let me calculate this. Density is equals to 7800. Specific heat is given 600. H is given as 20 and V upon area is 0.01. So if you calculate this, how much is the answer? Time constant, how much is the answer? Yes, that is correct. D is the answer anyway. So time constant you will get as 2340 seconds. 2340 seconds. Yes. Okay. So now this is 1000 upon 400. And let me put ln here. Ln here. Okay. And this is ये time I need to calculate, and this is tau dash, okay, which is equals to tau into 2340 seconds, 2340 seconds. And what you are going to get, tau is equals to 2144 seconds. Okay, is this clear? D is the right answer. Very nice. Shruti, are you able to solve this? Okay. Now, instead of this equation, look, I have told you this equation. This is the right answer. But instead of this equation, what equation? Ti minus T infinity upon t minus t infinity e to the power ha. Okay, 1 second, 1 second. It is positive only. Ha rho vc tau. Instead of this equation, let me write it like this: t minus t infinity upon t initial minus t infinity is equals to e to the power minus ha. I mean, you will get the same answer. There is no problem. But basically, this solves your problem much more because this value is usually negative. Okay, this value comes mostly, I mean, this value mostly comes out negative and it gets cancelled. Okay, so you can use either of them. There is no problem. Whatever you feel, I mean, I usually solve using this equation. Okay, but you can use any equation. There is no problem. Only I have swapped numerator and denominator. There is no problem. Answer, of course, will remain same. There must be no doubt. Okay, chalo. Let us go to the next question. Biot number signifies the ratio of. Tell me very quickly what is the right answer. I don't think I need to tell you this. Yes, very nice. B is the right answer. Biot number is internal conductive resistance. of conduction कहाँ होगा? Only in solids. And external convective resistance. And convection V happens in a fluid. Okay, so B is the right answer. Let's move on. Now, a steel ball, again, we have a steel ball of diameter 10 millimeter is at initial temperature, okay, I'll write it here. It is initial temperature 1000 Kelvin. Now it is required to be cooled to 350 Kelvin. That means this is your instantaneous temperature T by immersing it in water environment as 300. This is what T infinity. The convective heat transfer coefficient is 1000. That means H is also given. Thermal conductivity of solid is also given 40 K. The time constant for the cooling process. Look, they have directly given the time constant. Time constant is given 16 seconds. 16 seconds. The time required to reach the final temperature is final temperature. How much time it is going to take? Okay. Okay. Again, we have unsteady state. And what is the temperature distribution equation? Temperature distribution equation is T minus T infinity upon T initial minus T infinity is equals to e to the power minus HA upon rho Vc into tau. Okay. Can I also write this as e to the power minus tau upon tau star? Can I write this as like this? Okay. Now, this is 350. Okay, and surrounding temperature is 300 and initial temperature was 1000, and again this is 300 is equals to e to the power minus tau upon 16. Okay, I can write ln, ये कितना है 50 upon 700 is equals to minus tau by 16. Minus tau by 16. Chalo. So tell me what is the answer. Very nice. Very nice. There's nothing else. Just apply the ln log e and you will get it negative value. I think it is minus 2.64 is equals to minus tau by 16. Minus and minus get cancelled. Tau is equals to 42.22 seconds. Very nice. Shruti and okay. Okay. Are you able to solve this as well? 1 second is not the answer. If you are telling me to wait 1 second, okay. Chalo. Any doubt, Sean and Sahil? Any? Okay. Look, whatever questions I'm going to solve, I'm going to solve like 7-8 questions. You can solve other questions as well. Okay, but if you take book and start solving questions from there, then it will be complicated because those questions will not be asked in gate. So first of all, solve gate questions and understand what type of questions are asked in gate, and then solve similar type of questions from the book. Okay, chalo. Shruti, can we move on? Yes, 42.22 seconds. Very nice. Chalo. Next question. Now let us leave this question for some time. We will do this later on, or let's do it. Leave it. Let's do this. 2016 2 marks question. Now this is the only question that have been asked till now on the concept that I have told you in the beginning. Sean, you were there, right? Shruti and Sean were there. Sahil was not there. The only question that have asked, yes, error function one. Okay. The only question that they have asked till now based on that differential equation is this only. Okay, chalo, theek hai. We have two cylindrical shaft A and B at the same initial temperature. So T initial is same. Okay, shaft A and B, T initial is same, are simultaneously placed in a furnace. The surface of the shaft remain at the furnace gas temperature at all times after they are introduced into the furnace. The temperature variation is in the axial direction of the shaft can be assumed to be negligible. Okay, only in the radial direction heat transfer is happening. The data related to shaft A and B is given in the following table. Okay, so shaft A, shaft B diameter is given, thermal conductivity is given, and volumetric heat capacity is given. Now they are asking the temperature at the center line of the shaft A reaches 400 degrees Celsius after 2 hours. After 2 hours. तो ये क्या है? Tau of A is equals to 2 hours. And this is basically your temperature, 400 degrees Celsius, instantaneous temperature. Now the time required for the center line of shaft B to attain the temperature of 400 degrees Celsius. So for shaft B temperature is also 400, but I need to find out how much time it is going to take to reach that temperature, Okay. Now tell me what was that equation. You see, T minus T initial upon T infinite minus T initial is equals to error function x upon 2 alpha time tau. Okay, now it was a rectangular slab, that's why we said r, but even for a cylindrical body we can take it as we took it as x, but for a cylindrical body we can take it as r. Okay, chalo. Now tell me, look, if I talk about shaft A, okay, so what is T of shaft A? 400 minus initial temperature. They have said it is same for both the bodies. Okay, then T infinity is also same for both the bodies, and initial temperature is also same. Similarly, can I say shaft B? Shaft B, again I need to reach this temperature, so T is equals to 400 minus initial temperature, T infinity minus initial temperature. Okay, now because for shaft A and B, T initial and T infinity is same. They have given in question T initial is same for both the shaft, and they are simultaneously placed in the furnace. That means T infinity is also same. Okay, so that means this side for shaft A and shaft B is same. This side of shaft A and shaft B is same. So in order to satisfy this condition, can I say error function? Can I say error function of shaft A? 1 second. Error function of shaft A is equals to error function of shaft B. Can I say that? Because the left hand side is same, that means right hand side will also be same, isn't it? Okay. So what is this? This is R. Error function can also be cancelled, and I'll get RA 2 upon under root alpha A tau A. And that is RB 2 alpha B tau B. Okay. This and this will get cancelled. Okay. So can I say tau B? That is the time that the shaft B will take, at which the center line will go to 400 degree Celsius. RB by RA. So if I remove the under root, I can say it is square into alpha A by alpha B into tau A. Now I need to find out alpha A and alpha B. So this is Ka upon rho Cp. Alpha B is equals to Kb upon rho Cp. Okay. So this is volumetric heat capacity. Volumetric heat capacity. Okay, so we know the values of Ka. This is 40 and 20 and 2 into 10 to the power 6, 2 into 10 to the power 7. Okay, so I can find out this. For A, it is 40 and 2 into 10 to the power 6. So can I say 40 upon 2 into 10 to the power 6? So it is around what? 20 upon 10 to the power 6 meter square per second. And for KB it is 20 upon 2 to the power 7. 20 upon 2 into this. So I can say 1 upon 10 to the power 6 meter square per second. Meter square per second. Okay. So I can put the values here. RA, RB and RA is also given. Radius is also given. 0.4 and 0.1. Okay. So I can say 0.1 by 0.4 square into this is 20 and this is 1 because 10 to the power 6 will get cancelled. Okay. Into it is taking 2 hours. Time is 2 hours. Okay. So when you solve this, tell me very quickly what is the answer. What is the answer? I think this is 1 upon 16 into 20 into 2. And this is 8. Yeah, it is 2.5 hours. That is true. Look, I know it is slightly, different question, but very rarely they are going to ask this. Okay. And it is, as I told you, only once till now they have asked this question. But if they have asked, then we must know. There is no other choice. Okay. Even if they have asked once in last 30 years, then at least we need to know the concept. We cannot skip that concept. Okay. If that's why I say prepare for the worst and hope for the best. Hope that this type of question doesn't come, but even if it comes, you must know the concept. There is no other choice. Okay, chalo. Now rest of the questions are easy. There is no problem with rest of the questions. Okay, chalo. Let us move on. Now, now we have cylindrical steel rod, and this is the diameter and length is 0.2 meters. In first heated to 750 degrees Celsius and then immersed. So this is your Ti. This is your Ti. Okay, and then immersed in water bath at 100 degrees Celsius. So what is this? Can you tell me what is this 100 degrees Celsius? Yes, T infinity. Very nice. The heat transfer coefficient is given. Density, specific heat, and thermal conductivity is also given. The time required for the rod to reach 300. Now, what is this 300? Tell me. What is this 300? T instantaneous or simple T. Yes, right. Okay, chalo. Bhaiya, it is unsteady state. Whenever you see time term in the question, you'll understand it is unsteady state. Okay. And we know the temperature distribution equation. Ti minus T infinity upon T minus T infinity is equals to e to the power HA upon rho Vc into tau. ln ti, t इनिशियल कितना है 750 है, t infinite is 100, instantaneous is 300, minus infinite is 300, and I need to find out h rho. H is how much? H is given 250 into rho is 7801, C is 473, and I need to calculate volume per unit area into tau. So what is volume per unit area? What is volume per unit area? Yeah, R by 2 or D by 4. Okay. So this is 0.01 by 4. So can I write 0.01 by 4, 0.01 by 4, okay, into tau. Now solve this very quickly. Solve this very quickly. Tell me what is tau. What is tau? Time. Yes, Sahil is correct. 43.3 seconds. Very nice. Although I have the answer as 43.5, but anyway, that is correct. Very close. Very nice. And round off to 2 decimal places. Okay. Yes, 49 to 43 point. Yes, okay. You can write that. What was after 43.49? What is after that? 49 what? 49.087. Okay, ठीक so it is 43.49. That is correct. Yes. Is it clear, Shruti, Shridev? Are you able to solve this answer? Did you get the answer as well? Yes, very nice. Shridev, are you able to solve this? Chalo, theek hai, let us move on to the next question. Again, a metal ball of diameter 60 millimeter is initially, tell me what is this? What is this? 220 degrees Celsius.
Hello, sir.
Yes, one second. Sahil, tell me.
Sir, I have one query, sir.
Yes, tell me.
Sir, if you go to the Hessler chart.
Yes.
Yes, sir. Sir, like in the question what we were discussing, so sir, actually I tried to solve the question where it has been given. So can you go to the question what you have solved previously? Where
Okay.
yes, sir.
Which one? First one, like the last one that you
No, no,
solved?
no. Sir, last second, sir.
This one. This one?
Sir, before that, sir. Before that.
Okay. Yeah.
Where is the two shops were there. Yes, sir. Second,
Yes.
go to the question, sir.
Okay. Yeah.
Sir, in the question they have given that the surface of the shards remain at the furnace gas temperature at all the times after they are introduced into furnace. And so I can say that when we are calculating that conduction by convective. So if the temperature is same, sir, so I can say that the H will be very big in that case, the convective heat transfer coefficient.
No, one second. We are not assuming lumped heat capacity analysis in this. This question that we have solved, it is
Yes,
not
sir.
based on lumped heat gas analysis.
Sir,
Are you trying to say कि sir lumped, like You said that K should be high. Is it that question? Why are
Sir,
you
actually,
applying?
I was trying to study like if we can solve it by the lumped analysis.
Okay. ठीक है. No,
Yes, sir.
but for lumped heat analysis, you should first of all understand that it is saying uh, initial temperature simultaneously placed in the furnace. The surface of the shaft remain at the furnace gas temperature at all times. ठीक है. Surface is always at uh, furnace temperature, right? Furnace gas temperature,
Yes, sir.
whatever the temperature in the furnace. So wall temperature will remain same. Yes, that is true. So what are you saying then?
So what I'm saying, sir, like here, if you see the Hasler chart, so I can say that the here the Biot number will be very much high for this one.
Hmm.
So in that case, the only factor which will be affecting the Ford's number.
Biot number is very high, and then
Then, sir, I can use the Fourier's number in that case.
Fourier number is what? Fourier number is alpha tau by LC square, right?
Right, sir.
Hmm.
So, sir, if I'm equating the Fourier number and I'm keeping it same, then I'll get the same answer as well.
If you are doing, you are keeping what? I don't understand. Sorry.
So, if
What?
I keep the Fourier number same for the shaft A and
Hmm.
B, then
Hmm.
I'll get the same answer, 2.5 hours.
By using Hassler chart, by using
Yes, sir. By using
lump heat
Hasler chart.
analysis.
Yes, sir. Yes, sir. By using Hasler chart, I'll
Okay,
get
so
the
you
same
have
answer.
Hassler chart. Do you have Hassler chart?
No, sir. Actually, I was having one table. Actually, in that at
Okay,
the
okay, okay,
back
okay,
they have.
okay. So from table you are verifying that answer. Huh?
Yes, sir.
Okay. So that is the reason they have given Hassler chart, no? So to directly calculate temperature distribution equation. This equation, if you know Biot
Yes,
number
sir.
and Fourier number, then you can determine your temperature distribution equation. So you will, from the table, you can read this value actually.
Okay.
है ना? From this table,
Answer.
you can read this value, and then you can find out that I think time as well. What are the values given in that table? I have actually seen that table, but I have not read that table because I don't think they are giving Biot number directly. Are they
No,
giving
sir, they're
Biot
not
number
giving the
directly?
number. It's just like with the
Ah,
line, we need to equate it, we need to calculate it, and then we need to plot it.
okay, you need to plot it. But
Yes, sir.
anyway, if you are getting same answer, that is good. But there is one thing. In this question, they are saying that two shafts remain at the furnace temperature. So the walls are at furnace temperature, isn't it?
Yes, sir.
And the temperature variation in the axial direction of the shaft can be assumed to be negligible. That data related. The temperature of the center line. Okay, wait 1 second. What is the temperature of the furnace? Temperature of furnace is not given. No. So this is 400. Center line is 400. So
Yes, sir.
what is happening here is in lumped heat analysis, we assume actually that the whole body is at uniform temperature, isn't it? That is the basic assumption for lumped heat analysis, that the whole
Yes, sir.
body, if this is the body, so if center line temperature is let's say 400, so this will also be at 400.
400, yes.
है ना? This is the basic assumption of lumped heat gas analysis. So we cannot apply lumped heat gas analysis in this equation anyway. Okay, that is why we took that approach that was earlier that I discussed earlier in the beginning. This one, when you were not here. This one, this one. अरे यार कहाँ गया? In the very beginning, you can see that. Okay, this one.
Okay, sir.
So
Sir, it's
this
okay.
is the
After the
most,
class, I'll
yeah,
go through it.
this is the most general equation, and we analyze this by using some error function. Okay, but Hassler charts, basically what they do is, Hassler chart, if you can calculate Biot number and Fourier number, so they will directly give you the time. So they will give you this value directly. They will give you this value.
Yes.
So you can calculate directly from Hassler chart. If you read this chart, then they will directly give you the value of temperature, distribution, or time. Now, actually, the thing is that I have not read Hassler chart or the table also. So I cannot tell you in confidence that how can you read the table. I have seen the table, yes, but what are the exact values they give on the top? Are they giving Biot number or Fourier number? I am not sure. So
So
how
this
to
way, what
read?
you have solved, that is very easy. Like this is the formula what you have given. That's very easy. It's quite easy to
No, no,
understand.
no. Yes, yes, it's easy to understand, but basically, in that is also, like what that is what I am saying. Why I have not read that chart? Now, there is a reason. The reason is that for gate questions, you will not be able to use that chart or table. है ना?
Okay. Yes, sir.
That chart or tables will not be available with you. You have to apply this formula either, or most, like at most what they can do, they will give you the chart, Hasler chart. Then only you can read it from there. But that is also a very, very, very rare case. That is why I actually did not went through that chart as well. Like, okay, that
Okay.
is not required. Okay, chalo,
Okay, sir.
although you, if you are able to read that, I have to read that, so that I will see how it relates this formula with that chart. So that is why I'm not able to answer that at this point of time.
Okay. Okay, sir. Okay, sir.
चलो ठीक है.
Right, sir. Yeah. Thank you, sir.
No problem. चलो next question. So this is Ti. This is Ti. Now the ball, okay, the metal ball of diameter 60 millimeter is initially at 220 degrees Celsius. The ball is suddenly cooled by the air jet of 20 degrees Celsius. What is this 20 degrees Celsius? This is T infinity. Very nice. This is T infinity. The heat transfer coefficient is this. Specific heat, thermal conductivity, and density of the metal ball are 400. It is given. What is given? Specific heat, thermal conductivity, and density is given. Ball temperature after 90 seconds will be approximately. That means what is given to you? Now you need to find out the temperature after 90 seconds. This time tau is given to you, but you need to find out T. Again, what we will do by our general equation, we will not go away from there. T minus T infinity upon, or I can write it like this. Anyway, it's not a problem. I can write it anyway. Okay, HA rho VC by tau. Now this tau is known. I need to find out this T. Very simple. Very, very, very simple. Everything is known to me. Okay. Can I write ln T initial? No, this time I will not take ln. Why? Because I need to find out T anyway. So there's no point. T initial is 220 minus 20 upon T minus 20 is equals to E. H. What is H? H is 200. Area is how much? Achha, I need to find out volume upon area. And it is what? Volume upon area. R by 3 or D by 6. Okay. So again, this is 0.01 you will get. Okay. Because 0.06 upon 6. Okay. Chalo. So this is what? Upon density is how much? Density is 9,000. C is how much? C is 400. C is 400. Okay. And V upon area is 0.01 and tau is 90 seconds. Now, very quickly solve this. You need to find out this T. You need to find out this T. Tell me very quickly what is the answer. This is 1, 2, 1, 2, 2, 1, 900, 220, 200. Yes, that is right. A is the right answer. So you will get, I don't know how much value you will get, but when you solve this, you will get T is equals to 141 0.31 degree Celsius. Okay, so A is the right answer. What is अच्छा, that is 1.64. ठीक है 1.6487. I hope, I mean, I don't know if you are telling this, but ठीक है. Okay, not that. Okay, with E. Are you saying with E? Okay, ठीक है. This is 0.5. चलो, anyway, temperature is 141.31. Okay, चलो. Let us move on to the next question, and I think that is okay. Second last question. चलो. A small metal bead, again now radius is given initially at 100 degrees Celsius. Pi initially at 100 degrees Celsius. Let us take this question as homework. Very simple question. Similar question, nothing else. Okay. And GATE 2020 recent question, 2 mark question. You want to do it in homework? Same question what we have discussed now. Nothing new. Okay, try to do this in homework. Okay. Nothing new. Chalo. Last question. A hot steel spherical plate is suddenly dipped in a low temperature oil bath. Which of the following dimensionless parameters are required to determine instantaneous center temperature of the ball using a Hessler chart? Tell me very quickly what is the right answer. B is the right answer. Very nice. B is the right answer. Biot number and Fourier number. ठीक है, चलिए. So this was unsteady state, and now what you can do is you can refer to as look, concepts are covered, and as I have told you, there are mainly 3 concepts: temperature distribution equation that we have discussed. Okay, then lumped heat analysis, time constant, Biot number, Fourier number. These are the main concepts that are covered in this, and that is basically all the concept that is required for GATE. That is basically all the concept required for GATE. Okay. Now, what should be your approach? You must try to solve. If you have any workbooks, try to solve as many questions as possible from that workbook. See what you are doing wrong. Okay, if you are getting wrong answer. But the only thing you can look, the concept are covered. I would say there is no other concept in this. Okay, that is there are concept, of course, but that is not required for GATE. Okay, and if there are few concepts that must be covered by questions, that is a different story. But all the, I would say 99% of the GATE concepts are covered. That is my guarantee. Now what you will do, you will start solving as many questions as possible. Okay, whatever question you are getting from workbook, from any test series, from whatever you are getting, you need to solve questions, and it is the most critical part. Please do not rely on the questions that we have solved in class. Okay, it is not enough. I am telling you very frequently, if you keep solving these questions again and again, there is no point. Now, if you want, do it one more time. Do all the GATE last year 25 20 to 25 years question, that is, but just one time, and then keep it down. Start solving other questions, new questions, fresh questions from anything: workbook, book, reference book, test series, whatever you are getting. Try to solve more and more questions, and then in Jan, when you revise your concept, then again solve GATE question one more time. Okay, that should be your approach. Chalo. Now, what is the schedule for next classes? Let me tell you. Do you know what is the schedule? So tomorrow we have Thursday, right? Thursday, and the date is 24th. So 24th, Thursday, we are going to talk about heat exchanger first lecture. We are going to start heat exchanger. Yes. Then on Saturday, 25th, 26th, which is Saturday, we are going to talk about heat exchanger second lecture. And we will cover everything here for heat exchanger. Then 27th, which is Sunday, we are going to start radiation, heat transfer. Okay, so this is what we are going to do in the next 3 classes. Is it clear, everyone? Any doubt? चलो चलो बहुत बढ़िया, वेरी नाइस. चलो फिर let's say टाटा बाय बाय and please keep revising what we have already done. Okay, ऐसा नहीं है कि what we have already done you have kept it somewhere कि no I understand that I'll revise it before GATE exam. It is not going to work like that. Seriously, कितना भी अच्छा आ गया हो, even if you have understood everything perfectly, that you wouldn't have anyway, but even if you assume, even if you are thinking that you have learned everything perfectly, please at least do 2 or 3 revisions. Keep revising whenever you get time. You should come to a level that every subject you see, every subject, you cannot stop before every subject must be revised in 2 to 3 hours at least. These basic subject, I am not talking about what strength of material, theory of machine, these will take around 5 to 6 hours revision. But I would say HMT, I would say thermodynamics, I would say RAC, IC engine, power plant. I would also say I would here also production is not doesn't come into this. I would say industrial engineering as well. What other subject do you have? Um Theory of machine I have covered. Strength of material. What other subject do you have? Fluid mechanics, maybe a slightly, yeah, little more time, but again fluid machinery comes into this category. This all category is basically 2 hours, not more than that. Thermodynamics, let's say 2.5 to 3 hours. Heat transfer 3 hours maximum. You need to come to a level when you revise these subject 3 to 4 hours. Okay, unless you come to this level that you can revise all the subject in this given time, your revision must not stop. Okay, that is the basic criteria. Okay, chalo theek hai. So I can only tell you, I mean that is what I can only do, but you have to do it yourself. Okay, chalo theek hai. Let's meet tomorrow, right? Tomorrow we are meeting at same time, so we are going to start heat exchangers and I am going to see you there. Thank you very much. Tada, bye bye. Thank you so much.